My name is Edward Kasule MCC, a BA tutor for communication satellites, which is the first of 6 modules in the course, Satellite Communication and Radio Regulation for CDS. It is projected that by close of 2020, there will be more than 2,500 satellites in orbit around the Earth, providing all sorts of different services and applications to humanity. The International Telecom Satellite Organization, ITSO, and the other international satellite organizations continue to play an important role in the orderly development and equitable use of satellites for rural communications, broadband, and other essential services. The full course consists of the modules displayed in this slide. The red circle indicates where we are at present. You may wish to zoom in, look at details of all the 6 modules, or simply flip over to the next slide to look at the outline of Module 1. Module 1 outline is displayed in this slide. It has birth of satellite and satellite launches, orbits, radio waves, signal noise and spectrum, modulation, propagation, space and ground segment with all the sub-bullets, evolving technologies, and technology trends. In this first part of Module 1, we are looking at the first 2 topics in the outline, i.e., birth of satellites and satellite orbits. The other topics will be handled in subsequent videos in the same outline. The first satellite was launched in 1957 by Russia and was nicknamed Sputnik. Intelsat 1, nicknamed the early bird for the proverb "the early bird catches the worm," was the first satellite to be placed in geosynchronous orbit on April 6, 1960. We shall look at different types of orbits, including geosynchronous orbit, later in the video. In this slide, you see in the picture on the right of the screen a typical communication satellite as it would look in space with its solar panels and antennas deployed in operational position. The left simplified drawing, which is not to scale, shows transmitting and receiving antennas on a satellite pointed towards Earth, covering spot and global footprints or beams. We shall explain these terms in subsequent videos of this module. The drawing, which is not to scale, explains two important points about how satellite communication works. A satellite communication system comprises of at least 2 earth stations and 1 satellite. A complete satellite link comprises of an uplink and downlink. This slide talks about different uses to which communication satellites can be put, and also introduces some new terms and acronyms such as FSS, MSS, or BSS. The satellite communication industry uses many terms and acronyms. You may want to search for the meanings of these terms on the IT website or other sources. The more than 2,500 satellites in space, which I mentioned earlier, are not all communication satellites. As you see from this slide, satellites have at least 6 other uses other than communications. Please take time and read through this list. You'll find some familiar day-to-day terms such as GPS, which, as you know, is an application we all use for finding our location or the way to other locations. Did you know, by the way, that the Hubble Space Telescope is one type of satellite orbiting the Earth 15 times a day at 547 kilometers? In the previous slide, we saw 3 main categories of services provided by communication satellites. Slide 10 and the one after it go deep and break down these categories into actual services, including some helpful graphics for remembering some of these terms, such as the graphic of DTH, which means direct to home. It looks familiar, does it not? You can try and do a search on the unfamiliar acronyms. Slide 11 provides an even more detail about various satellite services in general. Indeed, the distinction between communication application, as we understood it yesterday, and other applications as they emerge today is becoming somewhat blurred. In a previous slide, we saw the numerous uses of communication satellites. But you might want to ask, why use satellites when there are other, more earthly alternatives? This slide answers the question. The benefits of satellites, to mention a few, are cost advantage, effects of natural conditions are tackled, quick implementation, which is very important for disaster recovery, alternate routing or redundancy, cost is independent of distance. This slide brings out a very important point. The major infrastructure technologies are complementary to each other. When a submarine or landline optical fiber is cut, or when it is required to provide cellular services or internet in a sparsely populated area, satellite is usually a first port of call, so to say. In the next slide, which I've put on the screen, we shall address ourselves briefly to the business and technology of building and deploying satellites into orbit. This is a whole separate industry from satellite communication, but it would help to know a little bit about the industry. Building and launching a communication satellite. It takes about 3 years to get a GEO communication satellite built and launched. Satellite payloads are customized for a given mission. Satellites are heavily tested on the ground in facilities that reproduce the space environment. Typical cost of a geostationary satellite is $150 to $250 million. This slide shows in graphical form the different stages of launching a satellite. We are not going to go into details of this, but another overview of the same stages is shown in this slide, which I am presenting. And the next slide. I'm afraid there's not enough time in this module, and indeed in the entire course, to delve into the complex subject of satellites, which, as we already learned, is a whole different ball game from satellite communications. Let us remind ourselves that we are communication engineers or technicians, and not rocket or satellite engineers. We shall wind up the study of satellite manufacture and launching with some FAQs, frequently asked questions, in this slide and the slide that follows. The questions. How are satellites fixed during operation? How does the satellite get its power? How much power does it take to transmit a signal? Who invented the concept of satellite communication in GEO? When were satellites invented? How big is a satellite? How many years can a satellite last? All these are questions frequently asked, but whose answers have been provided in these 2 slides. Now turn back to the topic of orbits, which, as I promised at the beginning, the second topic of this video. The slide displayed summarizes in a very graphical way the topic of orbits. You have LEO, MEO, GEO, GSO. LEO stands for low Earth orbit. MEO stands for medium Earth orbit. GEO stands for geostationary orbit, and GSO stands for geosynchronous orbit. Let me explain GEO and GSO. Geosynchronous. An Earth satellite whose period of revolution is equal to the period of rotation of the Earth about its axis. Let me also explain geostationary. A geosynchronous satellite whose circular and direct orbit lies in the plane of the Earth's equator, and which thus remains fixed relative to Earth. By extension, a geosynchronous satellite which remains approximately fixed relative to the Earth. As we shall see later in the course, the different types of orbits are very important for satellite communication industry, and I would advise the learner to spend some time studying the comparisons in this slide. The most fundamental advantage of GSOs is that they are stationary relative to a point on Earth. A transmitting antenna on Earth can be pointed to the satellite and vice versa without worrying about tracking. Another key advantage is that because the orbit is so far away from the Earth, the GSO satellite can see much more of the Earth than a LEO or MEO. Indeed, as Sir Arthur Clarke proposed way back in 1945, only 3 GSO satellites are needed to cover the Earth. On the other hand, because MEO and LEO are so near the Earth, and because radio waves travel in straight lines, you will need a constellation of tens or even hundreds of MEOs or LEOs to cover the Earth. All the 3 orbits are used for satellite communication. You'll see in this slide that low Earth orbit applications include Earth observation, International Space Station, satellite communication using constellations of satellites. You also see that medium Earth orbit is used for navigation, such as GPS, Galileo, and others. It's used for satellite communication, again using constellations. And you also see that GEO, geostationary Earth orbit, is used for satellite communication and meteorology. At this point, it is useful to go back to an earlier discussion of application of satellite and expand our understanding of the subject. In spite of their numerous disadvantages compared to GSO, LEOs and MEOs are increasingly becoming important for communications. Although we mentioned earlier that GSO satellites are stationary and remain in the equatorial plane, this was an oversimplification. The GSO satellites, indeed, when left to their natural forces, move east-west and north-south in a figure of 8 centered on their nominal position on the equatorial arc. As will be seen later in the video in this module, the spacecraft. Yes, we introduce this more general term, whose definition you may wish to do an internet search on. The spacecraft has boosters which nudge the satellite back on station. You can do more search on this if you wish. When the fuel is about to run out, the satellite controller may decide to allow the satellite to drift further south or north over a 24-hour period. The satellite is then said to be operating in inclined orbit, which is what this slide is illustrating. As shown in slide 23, earth station antennas have to track an inclined orbit satellite. Otherwise, there would be mispointing and link failure at particular times of the day. Let's now talk about orbital slot registration. The ITU member states have established a legal regime which is codified through the ITU Constitution and Convention, including radio regulations. In 1988, the ITU acknowledged that all countries, including lesser developed countries, have an equal right to orbital slots. However, Article 2 of the Outer Space Treaty forbids any claim of sovereignty by any country in space which will not allow countries to establish dominion over slots above their territory. At conferences in 1985 and 1988, the ITU did give all countries the right to an orbital slot directly over their territory, which would ensure at least some kind of satellite to all countries. As you can observe from the next slide, the equatorial arc, what we call the satellite arc, GEO arc, is very congested. Because the GEO arc is very congested, there's need for higher capacity, and also because the GEO arc introduces more latency. These two reasons have spawned a need for deployment of more and more LEOs and MEOs. And examples of these satellites in practice include O3b, which is now fully owned by SES, which provides higher capacity, greater coverage, and lower latency. As we noticed in our study of satellites so far, the space is crowded with satellites for all sorts of applications. And if there was no referee and there were no rules, everyone would suffer from interference, radio interference. You will study in some detail how the space user community does the refereeing and through ITU later in this course. This slide is simply an overview of the topic of orbital resource and radio frequency control, and the slide shows that this process involves allocation, coordination, power limits, and regulatory protection. Before we conclude this video, I will request you to test yourselves by attempting the question in slide 29. The question is, which of the following are false about geostationary Earth orbit communication satellites? Please test yourself. We have covered a lot of ground on satellite and their orbits. Though our main interest is satellite communications, we covered history, launching of satellites, introduced concepts of uplinks and downlinks, various uses of satellites, benefits of communication satellites, different types of orbits, fundamental advantages of GSO satellites, inclined orbits, control of interference, and we introduced the role and importance of international organizations such as ITU and ITSO. Along the way, we answered some frequently asked questions. Thank you for listening to me. The next series of videos in this module will cover radio waves, RF signals, and modulation. See you then.